Chapter 4, chemical quantities and aqueous reactions. You good with this? Okay. They'll catch on later. So you've heard of the greenhouse effect?
Yeah.
Yeah? Okay. So greenhouse gases, we think, oh, that's bad. But actually, if we didn't have any greenhouse gases, life could not exist on the planet because we need them. They're kind of like an insulating blanket. So the trick is, of course, you want the blanket to be warm enough, but not too warm. So what they do is they allow sunlight to come in and warm the earth, and then they prevent some of that heat from leaving. And it's a balancing act. So scientists have measured average temperatures, and they've determined that there's been an increase in the average of 0.7 degrees Celsius since 1860. You guys heard of global warming, right? And everybody makes it out to be this huge deal, right? Personally, I don't think it's that much of a big deal. It's something we should be aware of, and we should try to cut back on stuff, but I don't think we need to panic. And if you look at the temperature here, average temperature, you see that there's a lot of fluctuation from year to year. The blue here is the annual average. And then the red is a 5-year mean, so they take a rolling average. And so, yeah, it's gone up here, but 0.7 degrees, right? So that's not a huge change. Well, you can also measure atmospheric carbon dioxide, and we see there's been a large increase in atmospheric carbon dioxide, 38% over the same time period. So you see these two trends, and then you have to ask some questions about these. Is the increase in carbon dioxide causing the increase in global temperature? It could be. It could be the other way around. They could be unrelated. But those are the sorts of things that scientists have to think about. Well, what we can do is look at where is the CO2 coming from. And of course, one of the sources is from humans, human activity, the combustion of fossil fuels, so burning gasoline and oil and coal and things. And this is a representative chemical equation for the burning of octane, which is one component of gasoline. It uses carbon dioxide and produces a significant amount of carbon dioxide. But there are other sources of CO2. Another one is volcanic action. Volcanoes are spewing carbon dioxide into the air all the time. So how could we tell whether this global warming that we're thinking is due to the increased CO2, is this natural from the volcanoes, or is it from our use of fossil fuels? Well, we would need to measure somehow the amount of CO2 given off by volcanoes and the amount given off by the combustion of fossil fuels. Now, is that going to be a very, very precise, accurate number? No. You can't measure that very, very carefully, but we can get some approximations. So, chemical equations give us the relationships between the amount of fossil fuel burned and the amount of carbon dioxide emitted. So this reaction tells us that for every 2 molecules of octane, 16 molecules of CO2 are released. So that's in terms of numbers of particles. We can also scale that up and say 16 moles of CO2 are produced for every 2 moles of octane that are burned. So the coefficients that we learned to add to chemical reactions to balance them, the coefficients give us relative amounts of moles of each substance. Not masses, but moles, because the chemical equation describes the interaction between particles. Oh, that was a new section. Oh, well, I'll just put these together. Is that okay with you?
That's all right.
Yeah, he's my audience today. So, reaction stoichiometry. Studying these numerical relationships between chemical quantities in a reaction is called stoichiometry. And the basic idea here is, we've got the law of conservation of mass. What we start with, we end up with, is just the particles being rearranged. And so we can balance the equation by balancing the atoms, and then we can use that equation to predict what's going to be formed or how much reactant will be used. So I hope you guys had lunch, because we're going to talk about pizza, but we're not going to have any pizza to eat. let's think about making pizzas, and we're just going to be really, this has been a rough day, you're coming home, you're going to make some pizza, but you're doing it the easy way. So you bought crust, and you bought some tomato sauce, and you've got some cheese, and you're not going to do anything fancy. So you need 1 crust and 5 ounces of tomato sauce and 2 cups of cheese to make 1 pizza. And so we can write a chemical equation for making pizza. It's a lot like a recipe. It says we need this much of this and this and this, and this is what we get out. Recipes say, well, you need all these ingredients, and your yield, or you make 5 pancakes or whatever. We can look at this numerically as ratios. 1 crust to 5 ounces of sauce, 5 ounces of sauce to 2 cups of cheese, 2 cups of cheese to 1 pizza, or any 2 combinations in there. So we can use this to figure out how many pizzas could we make from 10 cups of cheese, assuming we had enough of the other stuff. Well, how many could we make? 5. So how did you get that number? From the ratio. You need 2 cups of cheese to make 1 pizza. So she took 10 cups and divided by 2 in her head. Got 5. We need to be able to write these things down, because it's easy when we're talking about pizza. It's not so easy when we're talking about octane and carbon dioxide and grams. So 10 cups of cheese, and we're going to use the ratios that we get from the equation. There's 1 pizza can be made for every 2 cups of cheese. And we just put the ratio in there so the units work out, and we end up with 5 pizzas. Any questions?
Wouldn't your ounces of tomato sauce have to increase as well?
Yeah, wouldn't your ounces of tomato sauce? We're assuming that we've got plenty of tomato sauce. And we'll talk in a few minutes about what to do if we don't have enough tomato sauce, because that's not always true. So in a balanced chemical equation, the ratios of the coefficients give us ratios of moles of each compound. And these conversion factors, these mole ratios, can be used between any 2 substances in the reaction. It could be 2 reactants, it could be a reactant and a product, it could be 2 products. And so the nice thing is, you might have an equation that's got 3 reactants and 5 products. But you can convert from any one to any one of the others in 1 step. So it's pretty cool. So let's look at making molecules instead of pizzas. If we burn 22 moles of octane, how many moles of CO2 form? So here's our balanced chemical equation. I like to use that to organize the information in a stoichiometry problem. So here I've got 22 moles of octane. What I like to do is find octane in the chemical equation, and below it write how much there is. So 22.0 moles. And then the question is, how many moles of CO2? So I find CO2, and under that I write a question mark for how many, and the unit is mole. So I can go from moles of one thing in a chemical equation to moles of another thing in 1 step. So I've got 22.0 moles. It becomes important to say moles of what? So we need to write the C8H18. And we want to convert to moles of CO2. And so we're going to put moles of C8H18 in the denominator, so they cancel out. The mole ratio comes from the balanced chemical equation. It's the coefficients. So 2 octane, that means 2 moles of octane. So I put a 2 in front of octane, and 16 moles of CO2. So 16 goes in front of CO2. And yes, you could reduce that fraction, but why? Sometimes when we do things like that in our heads, we screw up. So I prefer to just punch it through in the calculator. And I get 176 moles of CO2.
Where'd you get the 2 moles?
That's a good question. Where did I get this 2 moles? Right here, this 2. So you can think of it this way. The equation is saying 2 moles of this, 2 moles of that, react with 25 moles of that to make 16 moles of this and 18 moles of that. And so we have ratios between everything. So I get 176. My starting number had 3 significant figures. This should have 3 significant figures. How about the sig figs in the coefficients?
Those are absolutes, right?
They're exact. Because mole is a counting number, and so these actually come from numbers of molecules. It's 2 molecules of this react to form exactly 16 molecules of that. It's like counting people, right? There are exactly 6 children in my family. So that's nice, mole to mole conversions, but we usually measure things in masses because nobody's invented a balance that'll measure things in moles. So the stoichiometric ratios are moles only. So we have amount in moles to amount in moles. This is the mole ratio from the balanced chemical equation, but we have to take the mass that we're given and convert to moles using the molar mass. And then when we find the amount of the thing we're looking at in moles, then we use its molar mass to get the mass. So the path is grams to moles to grams. And what we'll see is that there are variations on that, but they're all variations on this theme. And so you need this as like a mantra for stoichiometry: grams to moles to grams. Grams to moles to grams. And that's your go-to path. And then you can tweak it if you need to, okay? You can't switch it around. You can't go moles to grams to moles. That never works. The moles are always in the middle. So let's do an example with that. According to the U.S. Department of Energy, the world burned 3.3 times 10 to the 10th barrels of petroleum in 2013. The equivalent of approximately 3.7 times 10 to the 15 grams of gasoline. Calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. So barrels of petroleum, those contain a wide variety of chemical compounds. And so they've done an approximation and said that would be similar to this much gasoline. Well, gasoline is also a combination of different hydrocarbons. And so we're going to use this as a representative equation. So there's a lot of approximations in this calculation, but it's still useful. So here's our balanced chemical equation. We read the problem. Well, I read the problem. What about those barrels of petroleum? Do we need to do anything with that number? No. This is the number we want. 3.7 times 10 to the 15 grams of gasoline. Well, gasoline doesn't show up in this equation, but we're saying we'll use the combustion of octane. So we're going to put that in for the mass of octane. And this problem has a little more backstory than most of the problems you'll see. Is just to go along with the story that the author is doing in the chapter. So we have that many grams of octane, and they want to know the mass of CO2. So the question mark here doesn't specify the unit. What would be a good unit? Grams. That's going to be the easiest thing. Grams. We're going to go grams to moles to grams. So when you first start doing stoichiometry, you should write the path out with the formulas. So we're going to start with grams of C8, H18, and then we're going to go to moles, grams to moles, moles of C8, H18. Then we're going to convert to moles of the thing we're trying to find, the CO2, and then grams of CO2. That's a funny element. The oxygen and the water are there, but we don't need to do anything to them or with them. We don't have to go from this to this to this. We just pick the one we're given information about, the one we're trying to find, and ignore the rest of them. So grams to moles to moles to grams. Notice that in this first conversion, I'm changing the unit, grams to moles. I'm not changing the substance. It's still octane. In the middle one, I'm not changing the moles, but I am changing the substance. And in the end, I'm changing the unit, but not the substance. So each of these, we're changing one thing. You can't do more than one thing at a time. So now that I have my path, I can write out my equation. So 3.7 times 10 to the 15th grams of C8H18. I know it gets tedious writing the chemical formulas out all the time, but just deal with it. Grams to moles of CO2 to grams of CO2. The units here in the path are the units on the top of my equation. 3 arrows, 1, 2, 3, 3 conversion factors. Then I take the previous unit and I put that in the denominator of the next factor so that the units cancel out. I'm going to put moles of C8H18 down here and moles of CO2 down here. So all the units work out. Any questions? The mole to mole ratio comes from the coefficients. There's the 2 in front of C8H18. So I'm going to write 2 in front of moles of C8H18. 16 in front of CO2. So I'm going to write 16 in front of moles of CO2. So that's the part we just learned how to do. This part, using the molar mass, we've already been doing. So we need the molar mass of octane. And I would encourage you to write it out, show your work, because it's so easy to make a mistake. So we've got 8 times the mass of oxygen. No, that's carbon. There's no oxygen in this. Maybe I need some oxygen. Plus 18 times the mass of hydrogen. So 8 times 12.01 plus 18 times 1.008. So my calculator shows me 114.224. And that's grams per mole. Technically, that would have 4 sig figs. I'm just going to keep the extra 2 along. It won't hurt anything, and it might help. So 1 mole of octane weighs 114.224 grams. Whoops. Okay? Then we need the molar mass of CO2. So that's 12.01 plus 2 times 32. It comes out to be 44.01. I don't think we need too many more illustrations of how to calculate a molar mass. No, that's okay. 3.7 times 10 to the 5th. Divided by 114.224. What did I say? I punched in 15. Okay. 3.7 times 10 to the 15th divided by 114.224 times 16 divided by 2 times 44.01 equals. So how many significant figures should our answer have? 2. So there's my 2, and then I'm going to keep 2 extras, and this is times 10 to the 16th grams. And then for a final answer, I'll round it. 1.1 times 10 to the 16th grams of CO2. Did you guys get that number?
Yeah.
Okay, good. Any questions? And so then they're suggesting that we should compare that result with the CO2 produced by volcanoes, which is about 2 times 10 to the 14th grams. So not as much, but just looking at those numbers, it's a little hard to say how are they related to each other. So what we can do is maybe do a ratio and find out how many times larger is the amount of CO2 produced by petroleum combustion. So we could take the CO2 from petroleum combustion and divide by the amount produced by volcanoes, and we come up with 55. So that tells us that petroleum combustion produces 55 times more CO2 than volcanoes do. Is that significant? Yeah, that's pretty significant. So there's definitely a possibility that petroleum combustion by humans is causing that increase in CO2 and probably that small increase in temperature. Any questions? Let's do another example. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, primarily HCl, according to this reaction. What mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? So all of this stuff at the top is backstory, basically. Why might we be interested in this calculation? The heart of the question is down here, though. So what mass of HCl in grams? Well, that's the question. So under HCl, I'm going to put question mark grams. And then it says this dose has 3.26 grams of magnesium hydroxide. 3.26 grams of the magnesium hydroxide. So what I'm going to do for this one is I'm going to go grams of this to moles of this, to moles of HCl to grams of HCl. So grams to moles to grams. Do you need me to write the path down? Okay. If you struggle with stoichiometry, go ahead and write it down. 3.26 grams of magnesium hydroxide. So grams of that to moles of that. To moles of what we're looking for, moles of HCl, and then grams of HCl. Grams to moles to grams. Then we fill in the units. If you're still struggling with dimensional analysis, please get some help. I'd be happy to help you. There's other sources of help as well. But it's not going to go away. It's only going to get, I wouldn't say worse, more important. And these stoichiometry calculations are essential to chemistry. Okay, so we've got all our units in place, and those tell us where to put the numbers. I like to do the mole-to-mole ratio first because it's so easy. So I look at the balanced chemical equation. In front of magnesium hydroxide, there is no number written. I understand that to mean 1. And so in the mole ratio in front of magnesium hydroxide, you could leave that blank, or you can write a 1 in there. It's all the same. In front of HCl is a 2, so I'm going to put 2 moles of HCl. And then we need molar masses. I don't know these off the top of my head, so I'm going to have to write it out. So magnesium hydroxide, magnesium 24.51, close, 24.31. 24.31 grams per mole. And then we have 2 oxygens. and 2 hydrogens. And this is one I screwed up on yesterday, so maybe I can get it right today. 24.31 plus 2 times 16 plus 2 times 1.008 equals 58.326. That's my molar mass for magnesium hydroxide. Molar masses are the mass of 1 mole. So there's always the 1 mole, and the number goes with the grams. 58.326. And then we need the mass of HCl, the molar mass of HCl. That one's a little easier. It's 1.008 for the hydrogen plus 35.45 for the chlorine. So I believe that's 35.456 grams per mole. So 35.45. Stop me when I do that. 8. Not paying attention. Eight. Okay. Now, I kind of hesitate to even mention this because sometimes when you suggest things like this and tell people not to do them, then they start doing them more. So I didn't tell the Monday, Wednesday class this, so we'll see if this helps or hinders you. Molar mass is the mass in grams of 1 mole of HCl. That's how we calculated this. This 2 does not come into the molar mass. A question?
Yeah, I got 36.
See, I fixed one part and I messed up the other.
I thought maybe you used less numbers, but no.
No, that's 36. And this is why we write things down. Because you write it down and you get the wrong answer, you go back and look at it and check and make sure you've got everything okay, and then you realize, oh shoot, I did something wrong. But the molar mass is the same that we've always used. The molar mass has nothing to do with the equation. No coefficients, nothing. It's the mass in grams of 1 mole of that thing. The coefficients only show up in the middle, the mole-to-mole ratio. That's the only place you put the coefficients. I was going to go to the next slide, but we need to calculate this. 3.26 divided by 58.326 times 2 times 36.458. How many sig figs? 3. So I'm getting 4.07. That's my third sig fig. 55 grams of HCl. And so as a final answer, I'll round that to 4.08.
You okay today?
That's a very good question. Am I okay today? I thought I was, but maybe not so much. Any other questions? I'm still upright, so that's good. It's always a plus, except when you're trying to sleep. Here's another one. A component of acid rain is nitric acid, which forms when NO2, which is a pollutant, reacts with oxygen and water according to this simplified equation. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year, assuming that there is adequate oxygen and water, which, there most certainly is. What mass of HNO3 in kilograms can form from this amount of NO2 pollutant? So lots of extra stuff in there. Just look for the numbers. So we've got 16 kilograms of NO2. So under NO2, I'm going to write 16 kilograms. And then what's the question?
The mass of HNO.
Mass of HNO3 in kilograms. So question mark? kilograms.
We could do a bunch of conversions between grams and kilograms and then from kilograms back. Or
Yeah, so he sees an issue here. We can't do grams to moles to moles to grams because we've got kilograms and we've got kilograms here. So here's the middle, the regular, grams to moles to grams. And we need to modify this. We need to convert to kilograms on the end, and we need to convert from kilograms to grams in the beginning. There's another problem coming up that's kilograms to kilograms, and so I'm going to show you a shorter way on one of them. The second one. Okay, so we're going to do kilograms of NO2 to grams of NO2, to moles of NO2, to moles of HNO3, to grams of HNO3, to kilograms of HNO3. Yeah, the unit thing kind of messes stuff up. It's okay. We can do this. So 16 kilograms of NO2. I'm going to convert that to grams of NO2. And kilograms of NO2 is going to come down here. So kilograms to grams. I'm going to go to moles of NO2. Grams of NO2 is going to be down here. For moles of NO2, I'm going to moles of HNO3. And previous unit comes down here, like that. And then I'm going to go to grams of HNO3, moles of HNO3 down there. And finally, to kilograms of HNO3 and I've got grams of HNO3 in the denominator. Any questions? Does it make your head spin a little bit? Why? Because it's probably not a very satisfactory answer.
no.
Because I said so.
Okay, that's
Is that better?
Yeah.
A little smidge, just a tiny bit. Okay, we need numbers. Mole ratio comes from the coefficients here. In front of NO2 is the number 4. So down here, in front of NO2, I'm going to write the number 4. It really is that simple. In front of HNO3 is the number 4. So in my ratio, in front of HNO3, I'm going to write the number 4. If you want to cancel those out, that's fine. If you want to multiply and divide by 4, that's fine also. I'm going to need some molar masses. But for me, the kilograms to gram thing is faster. So kilo means 10 to the third. So 1 kilogram is 1 10 to the third gram. This is K. Where's my pointer? Hello. There it is. K is a nickname for 10 to the third. Okay? So don't ever put them together. 1 kilogram is 10 to the third grams. Some of you are still a little shaky on this, as evidence from what you did on the exam. Over here I've got the K in the numerator. 1 kilogram is 1 times 10 to the third grams. Now, you may be able to look at this and see that this 10 to the third is going to cancel out that 10 to the third. We're going to pretend we don't see that. Now we need molar masses. So NO2. Nitrogen is 14.01 plus 2 times the mass of oxygen. I'm not going to do that in my head because I'll get it wrong. I should be able to do that, but 46.01 grams per mole. So 1 mole of NO2, 46.01 grams. And then we need the molar mass of nitric acid, HNO3, 1.008 for the hydrogen, and 14.01 for the nitrogen, and 3 times 16 for the oxygen. I'm not going to make you memorize molar masses, but you can see that knowing some of them speeds things up considerably. 63.018 grams per mole. I'm going to put that in over here. 63.018 grams to 1 mole. Any questions? I'm going to punch it through the long way on my calculator. 16 times 1 EE3 divided by 46.01 times 4 divided by 4 times 63.018 divided by 1 EE3 equals 29.14. No, 91. That should have 2 sig figs, and the unit is kilograms of nitric acid.
So you can just skip a lot of punching in, cancel out the thousands and the fours,
Yes,
and just do 16 times. I just did that and I got the same answer.
right. So you can look at this and say, well, 4 divided by 4 is 1. I can skip that. Those cancel out. And you can say, well, here I'm multiplying by 10 to the third, and I'm dividing by 10 to the third, and those cancel out. And so you can do that. But I want to show you the long way, because some students are not comfortable doing that. And in the story of the rabbit and the turtle, the tortoise and the hare, the tortoise always wins, doesn't he? It's because it's the same story over and over again. The tortoise just went slow and steady. And so this is what I think of as slow and steady. Just writing all of it out, that always works. For some of you, you can get good results with some simplifications, some shortcuts. But that's only okay as long as you're still getting the correct answer. So, any questions? Why is it so warm in here? That's my question.